Okay, so we're gonna talk about wave packets a little bit before we move on to um, identical particles. And the idea there, from last time was that the actual solution to a scattering problem is, of course, the time-dependent wave function, and it can be written in terms of the stationary piece as an envelope function, which is centered around your incoming wave vector. And then you stick in the stationary solution here. So this would be the stationary solution, which would include the incoming plane wave and the outgoing spherical wave. And then what you would do, and of course this depends on K. K is labeling the scattering solution, the stationary scattering solution, and that's sort of the incoming momentum. And you just have a distribution of incoming momenta, right? And what the whole time-dependent wave function, what it is just a distribution over all the different incoming momenta that are part of the wave packet. That distribution multiplied by what the scattering solution looks like for each of those modes. And you would say that this is normally sort of peaked at around some input wave vector, the sort of initial momentum that you give the incoming particle. And then the time dependence is just that each of these modes picks up a complex phase like that. And that's the solution. So in the case where you're just looking at the incoming wave, we saw the last thing I wrote down was what this looks like for the incoming wave. And the idea there is that you would just want to expand the incoming wave part and the phase that it picks up. You would want to expand this around the K0 value. And if you do that, Taylor series, we've sort of done these kinds of expansions before, what you end up getting is that if you expand out this phase around the K0 value, what you would get is that your coordinate just gets shifted by a velocity that's given by the initial momentum. And it's that velocity multiplied by t. And then there's also a phase factor that comes out. That's just an overall phase that depends on the initial momentum. But the point is that for the incoming wave, what this looks like is that there's just this there's this phase factor, and otherwise it looks just like the wave function at t equals 0, so your initial wave packet, right? But it gets translated by a velocity. So again, if you stick in a plane wave here for the stationary solution and you assume that, this envelope is peaked around K0, then you can expand the plane wave part and this phase around K0. And what you'd get is just that this wave function reduces to the wave function at t equals 0, so just your initial wave packet that you set up, and it just gets translated along by v0, the initial momentum that you give it, which makes perfect sense. You set up a little wave packet, and if there's no potential If you just have that plane wave solution, and then the wave packet will just travel along with whatever initial speed you give it. If you want to look at the scattering part, it's also pretty straightforward, because all you need to do is just replace. We know that the full solution is going to be what it is for the plane wave plus the solution that you would get for the scattered portion. So if this is the plane wave portion, then whatever is left over must be due to the part of the stationary solution that corresponds to the scattered wave. So in that case, the scattered portion is just going to be the integral. Again, we have an integral over different modes that contribute. And now we have the asymptotic stationary solution, which is, the scattering amplitude. We have k r hat, that's the direction we're looking, that's the k prime. It also depends on the incoming direction, and it's multiplied by a spherical outgoing wave. And again, there's this factor like that corresponds to the complex phase that it picks up. And again, what you do here is you say, well, okay, the wave packet is going to be dominated by modes around the initial momentum that you send in. So we expand around that initial momentum. What you see, it's a subtle thing. The more narrow your wave packet is in momentum space, of course, the more wide it will be in position space. So like if you really precisely specify the initial momentum, that will make your location a little bit more spread out. So there's a trade-off there, and that can matter. But under the condition that the wave packet is reasonably narrowly distributed in momentum space, we can expand everything around that initial momentum. And what we would get is, so k gets replaced with k naught, the initial momentum. And of course, the over r comes out. We get this integral d3k of the amplitude and e ikr minus I omega kt. So the scattering amplitude can come out, and again, we can do a Taylor expansion of this time k around k naught. See, it's a little bit different. Before we had a plane wave, which is k vector dotted into r, but now we have a spherical wave, so that's the magnitude of k times r. So you have to be a little careful, and you'll practice this kind of thing on the homework. So k, you can write it as, you can write it in a funny way. You can write it as k naught plus k vector minus k naught vector. And the reason you would do that is because, well, you know that the magnitude of k is just, of course, k dotted into itself square root, but you know that you want to expand. So this quantity is supposed to be small. So you want to be able to Taylor series this quantity around k naught. So this is like a trick to do it. You just add and subtract k naught. Then you do the Taylor series of that. And the first term, of course, if this is small, is just k naught, the magnitude, your initial wave vector magnitude. And then you have the second term, which is going to be k naught hat, that direction, dotted into k minus k naught. It's just a Taylor series for this. And if you look at that, this is nothing but k naught unit vector dotted into k, right? Because k naught unit vector dotted into k naught is just going to be k naught. So this cancels that, and you're just left with this term. So it's basically the k vector dotted into the initial direction that you're sending, which is going to be like along the z-axis typically. So now you can substitute this back in to the integral, and you get that the scattering form is, again, this scattering amplitude, and then you get the integral. And you have the amplitude, and you have E. What do you have up here? You have the E, I, R, and then you have the K naught dot K. And you have the minus I omega K T. So that's the same. But if we look at this, what is this thing? This has exactly the same form as our plane wave. Remember that our plane wave, what was that like? It was the thing in the exponent was e to the I k dot r minus I omega kt. Here we have something quite similar, except that instead of r, we have this guy, which is the magnitude of r times the initial direction. So, but that's still a vector. It's still, you know, a position. It's just not a position of where you're looking. It's sort of the distance out at which you look in the direction of the incoming beam, so along like z hat. But we can now approximate this integral using the same approximation we used for the incoming plane wave. The only difference is instead of r here, we would have the magnitude of r times k naught. But see, this is convenient because now in this case for the plane wave, this is r is like where we're looking, and that doesn't necessarily have to be in the same direction as where how the particle moves, because this is going to be along the z-axis typically, and then r is just like where we're evaluating this wave function. But now it's quite similar, except it's all along the same direction. So this whole thing is just using the plane wave result. It's going to be the original wave packet form evaluated not at r minus v, but everything's along the same direction. So it's magnitude of r minus v naught t, and it's evaluated along the k naught direction, the direction of the incoming particle, and it's the t equals 0 portion. And of course, there's leftover e to the I omega k naught t. This is just borrowing exactly the same approximation we had for the incoming plane wave. You see, instead of this, our vector, we now don't have r vector, but we have the magnitude of r times k naught hat. So if you do that, and then v naught's already along the k naught direction, so this just comes out as an overall magnitude times the k naught direction. So that's the scattered portion. But you see, it's quite convenient because you can now use this to evaluate like the probability that you observe a particle in some direction. So again, this looks just like the incoming plane wave, except the wave packet is kind of going in a different direction. But what you can do is now you can calculate the probability of observing a particle in some solid angle, omega out here is some detector. If you were to do that, what you would want to do is you would want to calculate, so this is sort of d omega times the integral of all the radial pieces of that wave function, so r squared dr, you would want to calculate this, the magnitude of the scattered portion. Squared. That'll just give you the probability, right? In a solid angle, it'll just be, we know that integrating the magnitude of the wave function squared is going to give us the probability for a fixed sort of solid angle or fixed angle. We'd want to integrate up over all the radial, over the radial direction to get the probability. So if we do that, that's pretty straightforward because there's lots of, well, I mean, we can just do this, right? This guy, actually, it doesn't depend on the radial direction at all. What is this amplitude depends on k naught and the r hat direction and just the k naught vector. So immediately this part comes out and you just get, f. And now I can just write it in terms of omega, right? It's just the scattering amplitude in that direction. Then there's a 1 over r, which gets squared and gets multiplied by this r squared. So the r squareds cancel, and you're left with just this integration from 0 to infinity of what of this initial wave packet function. So you get r minus v naught t, k hat t equals 0. And this is evaluated, just the magnitude squared, and it's dr integral. Okay, so, but that last bit, this part here, this is nothing but like the initial normalization of the wave function. So this must be whatever it is, since we're integrating over all r here, it's going to be just the entire density of the initial wave packet. So it must be the amplitude associated with the incoming particle. So that means we can identify the differential cross-section. The differential cross-section must be this probability of observing a particle in the solid angle divided by the total flux, that's coming in, from, your initial, whatever you're scattering, like your incoming beam of particles, what have you. So it must be the probability divided by the incoming flux, because the probability is going to be proportional to the normalization of the incoming wave. As if you send more incoming particles, the more get scattered. So the differential cross-section must be normalized by the, you must divide out by the total flux that's coming in. So it's actually this guy squared, that's the total flux. And so now you see that everything basically cancels, and what you find is that this is just, as we would expect, the scattering amplitude squared. So even if you use the wave packet description, the scattering cross-section still makes sense. You can still, it's still going to be equal to the scattering amplitude squared. So even if you go through the trouble of putting all your incoming particles in wave packets under fairly general conditions, namely that your wave packets are kind of narrowly distributed around a particular incoming momentum, then all of the formalism we developed for scattering still holds. So even though we didn't use the time-dependent thing, it's clear from this that if you were to use the time-dependent thing, then as long as your amplitude here, the wave packet envelope is narrowly peaked around k naught, then the time dependence really is pretty trivial. You can just expand these phase factors around the incoming momentum, and what you get is the same sort of deal, that your time dependent scattered wave function is just going to be proportional to the scattering amplitude, which just comes out of the integral. So then if you're doing something like calculating a cross section, it still works out to be just equal to the scattering amplitude squared. But it's still it's sometimes interesting to use this form to analyze what actually happens, in terms of the time dependence. You could still use this form to figure out, like, oh, well, initially I have a wave packet, it's gonna come in and interact with my target, and then it's going to come out. And you can figure out what the time dependence is by studying this integral, because this has all the time dependence in it. It's captured by these phases here. And all you need to do is to put in whatever solution you get for your target potential for the scattering amplitude here. And that's the only thing. And for, what's A of k? Well, again, it's just A of k is just your distribution of modes initially for your wave packet that constitutes your wave packet. So you typically take it to be some Gaussian. So this is modulo some normalization. This is going to be, some Gaussian centered around a k naught, which you typically put along the z axis, and then it's multiplied by the uncertainty in your location, your initial location, squared. So, again, so if you want this to be very narrow peaked, then you have to make delta x large. So there's a trade-off between how narrowly you can define the momentum and how much uncertainty you have in the incoming particle's sort of initial in its location. But yeah, so that covers scattering, and yeah, that's basically all I wanted to say about that. You'll have some practice on homework 5 doing these things. But any questions about scattering? You'll practice this wave packet description on a case where your scattering amplitude is large when you're near a resonance. So that'll be, you'll see what happens there. By the way, I think on this most recent homework, you should check out the homework 4 solutions. I think most people didn't get the shell scattering problem, but it's an interesting problem. The idea there is that you have a shell, and the shell is represented by a spherical potential barrier of size V naught. It extends from R to 3r over 2. So what that looks like is just at r, there's just a barrier, the barrier of size r over 2. It's like a thick shell. And then what happens, of course, if you send v naught to infinity, in the extreme limit, what happens is that any particle that tries to come in here, it'll just encounter a hard wall. So it'll be like a hard sphere scattering at radius 3r over 2. But that's an extreme limit. If you do things carefully and you make v naught large but finite, so that the particle can still, incoming particle can still tunnel in here and get into this region inside, well, then what will happen is that the particle can get trapped there. So if you send something in at an energy that's matches a bound state energy that lives inside the shell, because inside the shell it look like basically a potential well, right? It'll see there's a well in here, and so it'll have bound states which are formally only there when v naught goes to infinity, but they're still or that's how we identify them. But for finite but for large v naught, they'll still be sort of quasi bound states, even though it's true that the particle can always sort of tunnel out. But the point is that if you don't make v naught just formally infinite right away, but you send in particles at some energy that matches the bound state energy of which you would have had there if v naught makes sort of an infinite well, then what can happen is that the particle can get trapped there for quite a while. And so in terms of scattering, that leads to a resonance where your scattering cross section basically blows up because the particle gets trapped. So that's a kind of interesting phenomenon. I think most people did not catch that. So I would look at the homework for solutions, and you'll explore this phenomenon in a little bit more detail on this next homework by looking at the time dependence. And basically there, you see what will happen is you'll look at the wave packet description. And for the wave packet description, you'll look at a kind of wide wave packet. And so in some sense, the wave packet will kind of overlap the whole bound state region. And so your scattering amplitude or your cross section will actually kind of give you a hint about how long the wave packet stays inside that well. So, well, you'll see. So that's part of the new homework. All right. Anything else about scattering? Okay, so the last topic that we'll cover is identical particles, and that'll sort of lead us to a discussion of field theory and stuff. Because as soon as you have multiple particles, well, the kind of single particle quantum mechanics that we've been using breaks down, and you rapidly recognize that you no longer have a simple Hilbert space, right? But you need a separate Hilbert space for each particle in your system. And once you include things like relativity, where you no longer have a well-defined concept of like a fixed number of particles, and you can have like pair creation, for instance, at high enough energies, because E equals mc squared, so you can convert at high energies from say a high energy photon to a pair of particles. As soon as you have those kinds of processes which no longer conserve the total number of particles, then you recognize that the sort of fixed particle number Hilbert space is no longer appropriate. So you can't, it doesn't work very well as a description of the physics. So you have to move to a more complicated Hilbert space, which allows for the possibility for an arbitrary number of particles. And as soon as you do that, you recognize that the kind of quantum mechanical objects that you want to work with are no longer like vectors in a Hilbert space in the sense that we're used to, that describe like the state of a fixed number of particles, but rather they're quantum mechanical fields. So that's where we're going, but where we want to start, of course, is just what happens if you have identical particles. So you have identical particles, or if you have any two particles, we know in principle what to do. We sort of studied this last semester. We know that the Hilbert space is going to be a tensor product space between the Hilbert space associated with particle 1 and the one associated with particle 2. And so in principle, states in this Hilbert space are described by, whatever the state of particle 1 is and whatever the state of particle 2 is. But when you have identical particles, it's not so simple as that, because if they're truly identical, then the labeling, whether you call one of them 1 and the other one 2, or vice versa, that can't possibly change anything about the results of any measurement. So if, for instance, you're studying, if you have some state of these two particles, they're identical, some state psi, which is an element of this guy, and it could be in general some entangled state, then if you measure the states of the particles individually and ask, is particle 1 or in state A or B, then you can, of course, assign to that a probability of taking the state and measuring the states of particles 1 and 2. And that should just be the inner product between the state and the properties, the state associated with the properties that you're measuring. But of course, in general, as I said, the label doesn't matter. So the probability that you measure state A for particle 1 and state B for particle 2, that probability has to be the same as measuring state A for particle 2 and state B for particle 1. And in terms of the tensor product space, we know that that would look like the following, right? And in general, these are not equal to each other because, well, they're not. They'll just be, they're two different vectors. And if we dot them into our state, our prepared state, then it's not, generally speaking, it's not going to give you the same result. But it has to. So we have to set things up so that these two things are in fact equal for identical particles. They have to be equal. Because that's what we mean by identical particles, is that no matter how you label them, you can't tell them apart. So any kind of labeling you have shouldn't influence, any measurements or any probabilities that you calculate. So what that means is that you must have the most that can happen is that your vectors, when you flip the states of the particles, that at most what can happen is that they pick up a phase. So now we're going to denote, so this is going to be like the state of, so again, this is the state of particle quote unquote 1, and this is the state of particle quote unquote 2, but again, the label doesn't matter. So if you switch these things, then the most that can happen is that your state picks up a phase. So this is like a fundamental consequence of having identical particles, is that if you exchange their states, then most that can happen to your vector in your Hilbert space is that it picks up an overall phase. So if you switch the phases again, then of course you can pick up yet another phase. But now if you switch them back, you're back to where you started. So you have this constraint on the phases, namely that if you take this phase associated with switching it from A to B, plus the phase from switching it from B to A, that this must be equal to 1 identically. And so if I take the square root of that, then the sum of these phases must be equal to plus or minus 1. So that's the kind of consequence of what we must have. And you know that's physically, of course, these states are only defined up to a phase. So we can actually choose our identical particle states to be as follows. We can say, well, we're going to define these states where, particle 1 is state A and particle 2 is in state B. We're going to define them to be proportional to this phase that they could, in principle, pick up under particle exchange. So I'm going to define it as your original states multiplied by this phase factor. We're free to do this because we can define our vectors however we want up to a phase. So we can take our original vector and multiply it by this phase associated with what happens under particle exchange. That's just the definition. And if we choose these states, then we can look at what happens if you exchange A and B for these kinds of states. And so we can look at that. So this is equal to this. This, of course, if we flip A and B, then it'll pick up e to the I theta AB. So that combines with this theta AB over 2 to give me I theta AB over 2 with a plus sign, with these things flipped. And then I can, of course, put I can rewrite this guy in terms of this definition with the prime. And this will be e to the I theta AB over 2, e to the, I can multiply right by theta BA now over 2 and e to the minus theta BA over 2 BA. And I can identify this piece, right, as B A prime. Right, I'm just multiplying by 1. I'm just writing 1 as I theta BA over 2 times e to the minus I theta BA over 2, and identifying this piece as BA prime. And this piece is just combines. And so what we find is that when you exchange A and B for these new state definitions, you just get e to the I over 2 theta AB plus theta BA. And it's BA prime. Just those new state definitions. So if we look, but we already decided that this guy is plus or minus 1. So these states under particle exchange, flipping the states of the two particles, what can happen to them is that they either remain the same or they pick up a minus sign. And those are the only two possibilities. So the only two kinds of states we have are ones that change under particle exchange when we exchange the states of the two particles, and those are the fermions, and ones that don't, and that's those are the bosons. So the two possibilities are as follows. And see, all this just is completely determined by what we mean by identical particles. As soon as you say that we have identical particles, the properties of, quantum mechanical Hilbert space and what we would mean by identical particles, namely that if we exchange their states, then the only thing that can change in terms of the vector in the Hilbert space is that it picks up a phase. Under those conditions, all our states can be rewritten such that they are only one of two different things. Either they're ones that don't change under particle exchange, and that's the bosons. Otherwise, they pick up a minus sign, and that's the fermions. And we can always make that definition because of our freedom of choice for the overall phase of the state. We can always set things up so that our states are of this type. So that's kind of an interesting thing. Any questions about that? So you might have heard in like condensed matter and so on that people look at things that are neither fermions nor bosons, and things called anyons, which have more complicated properties. And it's true, if you want to do this more formally, you would actually have to have a better description of what you mean by exchanging A and B. You would actually have to think about the actual operation that would take you from this state to the one where the particles get exchanged. And the way, I guess a simple way to think about it is you have your two particles, and if you want to exchange them, then you could literally just rotate them around each other. So the particle exchange operation is just a kind of rotation. So it's really described by the rotation group in d dimensions. And in 3 dimensions, you recall, that's the rotation group is SO3. If you remember our discussion of angular momentum, there were only 2 different kinds of rotations that take you back to the same place, right? There was a rotation. There was sort of the trivial, you can think about it in 3D in terms of the plate trick or the belt trick, as it's called. But I sort of did that last semester, so I won't sort of repeat it. But as you recall, the whole point of that discussion was that the fundamental group of the rotation group in 3 dimensions is Z2, which is a group with 2 elements in it, 0 and 1. And those are like the rotations by 2 pi and 4 pi, if you want to think of it that way. And what that means is that what you're looking for, what does it mean that the two particles are identical, right? It means that when you rotate around, you get back to the same state. So you're looking for all the rotations that bring you back to the same state. And in 3 dimensions, there's only 2 classes of such rotations. It's ones which are characterized by this fundamental group Z2. And it's either the 0 rotation or the 1 rotation. If you want, think about it as in terms of the plate trick, it's either a rotation like this, where you rotate once by 2 pi, or it's a rotation by 4 pi, where you get both of those get you back to where you started, but obviously they're different from each other. And that corresponds to the 2 different ways of exchanging 2 particles. You either pick up a minus sign, that's the same as this rotation by 2 pi, or you don't pick up a minus sign, and that's the same as the sort of 4 pi rotation. You get back to the same place. So there's 2 classes of things, fermions or bosons. And that's what this thing tells you, is that in 3 dimensions, there's only 2 different kinds of ways of rotating 2 particles into each other. And those are that's what defines sort of fermions and bosons. Conversely, the fundamental group for rotations in 2D is actually the whole set of integers. Why? Because in 2D, you can imagine exchanging 2 particles, but you can sort of spin them around that central point as many times as you want. And those are all inequivalent ways of doing the particle exchange. And so what the fundamental group tells you is that in 2 dimensions, you actually get an infinite number of ways of doing the particle exchange. There's an infinite number of classes. And in principle, that means that when you exchange 2 particles in 2D, so this is 2 dimensions, this is 3, you can actually pick up an arbitrary phase. And these are so-called anyons. And that's why in condensed matter, people are so excited about surfaces and, topological insulators and things like all these exotic things that people talk about in condensed matter seminars. They have to do with lower dimensional behavior. They're not actually bulk properties of a 3D material. They're associated with states that occur at the edge, at 2D and 1D edges of materials, because at those edges, because of this topological property of the rotation group, you can actually get more exotic kind of particles with different particle statistics other than just boring fermions or bosons, as long as you are confined to 2 dimensions. So that's a little bit on the side. It's is just like for your own entertainment. But I thought it might be worth it to mention. We can talk more about it in recitation or something, but it's pretty outside the scope of the class. I don't really want to get into fundamental group stuff, but we can if there's interest. So yeah, that's a little bit on the side, but for our purposes, we'll only really be worried about the 3D case where we either have fermions or bosons. So all you have to remember is that under particle exchange, your state either picks up a minus sign, and then the identical particles involved are fermions. If the state doesn't change, then you've got bosons. So that's it. But any questions? Okay. So this kind of property of whether a state is symmetric or anti-symmetric is actually becomes completely generic, and all states have to be one or the other. And you can actually sort of prove that. You can imagine, so a symmetric state, what do we mean by a symmetric state? We mean that the coefficients of the state are the same. So this is for a symmetric state. It's for, you know, a bosonic state. And then for a anti-symmetric state, fermionic state, you would pick up a minus sign. So in principle, we sort of argued that those are two kinds of states we have, but you might wonder, can we construct a state that's kind of some linear combination of the two, right? You'd think that, well, you know, in Hilbert space land, we are allowed to take linear combinations, so why can't we just take a linear combination of these two kinds of states, and then we'll have some kind of hybrid state? So can we take linear combinations of these kinds of states? And we'll see that the answer is no. So suppose we did, though. So what would that look like? Well, there would be some coefficient. You know, let me call these phi's, I guess. These are the symmetric and anti-symmetric states. So suppose that, sort of without losing much generality, we can set the symmetric, we can take two orthogonal states that are symmetric and anti-symmetric. And we'll just say, suppose we constructed this linear composition where we have some coefficient of the symmetric piece, and we have some coefficient that's the anti-symmetric piece. We ask, can we construct such an object that's going to be a linear combination of this and this? But this is actually quite a bit of a problem, because if we take the inner product of this state with one of these basis states, A and B, what's going to happen? Well, what will happen is you'll have this coefficient, and you'll have that coefficient. And so now these guys, by these properties here, this will be equal to phi s psi. So this is the guy that doesn't change. So it's BA phi s. This guy picks up a minus sign. So, all right, so that's what would happen if we had such a linear combination. And this is a problem because this means that the state is no longer either symmetric or anti-symmetric under particle exchange, right? Because we showed that generally if you have identical particles, your state must be symmetric or anti-symmetric. And if we do this, we see that now, what is this thing? This is, of course, BA dotted into this original state. Well, no, sorry, not the original state, but it's all messed up. it's the original state with a relative minus sign between the two components. So let me write it. So it's BA, there's phi S, psi S, and there's a minus sign now here, phi A, psi, phi A. So there's this annoying minus sign between the two. So there's a change of sign here in the relative phases between the two components. And this is not possible because this would violate the whole idea of having identical particles. So we argue that if you have identical particles, then your states better be at most picking up a overall phase. And so this tells you that if you had such a linear combination of symmetric and anti-symmetric, then such a state would violate that. So you can't have these states, and so basically the only way that this can work is if either this is equal to 0 or this is equal to 0, and then it's fine. So we can't take linear combinations like that with of symmetric and anti-symmetric states, because in the end you're always going to have a state which is either symmetric or anti-symmetric. That's the only possibility. So you can't like transition between the two kinds. It means you have very strong selection rules. If you have one kind of state, you start with a symmetric one, you're not going to end up in an anti-symmetric one, and vice versa. And all your states are going to be classified as either bosonic or fermionic. And that includes all of the degrees of freedom. So it gets even more interesting when you have things like spatial degrees of freedom along with spin degrees of freedom. So that's sort of what we'll be considering. But any questions about that? So again, the idea is any state is going to be either one for which it's symmetric under particle exchange, namely these coefficients here. You can think of these as sort of the basis vectors, which we're expanding these size, and either the coefficients are going to be the same or they're going to pick up a minus sign when we exchange you think of it as exchanging the particle labels. So yeah, that's the only possibility, and that will have important consequences. Okay, so let's talk about wave functions for these kinds of particles. So even though it's even though we have these properties, it's still convenient to have labels on the particles. So we can still use the labels. We just have to properly ensure that our overall state is either symmetric or anti-symmetric under the particle label exchange. So one thing you can do is you can add labels, but then just fix up your state so that when you exchange those labels, you take one and change it to a 2, exchange the particle labels, that you either pick up a minus sign or you don't. And that'll be good, because then we can still kind of pretend, I guess, that the particles are labeled. It's just we'll always be able to we always just make sure we construct states such that they're either symmetric or anti-symmetric under particle exchange. So what do I mean by that? If we want to construct, say, a symmetric state of two identical particles in states A and B, what could we do? Well, and we call this the bosonic one. Well, we would just symmetrize this. Namely, we would take a linear combination of the state where we're going to say particle 1 is in state A and particle 2 is in state B. And we're going to have a linear combination with the opposite labeling. So you see, this makes perfect sense, because if we were to flip the labels 1 and 2, then these two states just transform into each other, and we'll get back out the same thing. So this is symmetrized, and we can still use these labels. It's just the overall state is symmetric under the switching of the labels. You can, of course, do the same thing and construct an antisymmetric state, which would be a fermionic state. That's the same thing. It's just you now add a minus sign. So by doing this symmetrization or anti-symmetrization, we can now think about these individual kets as just as if they're kets for distinguishable particles, because we've fixed everything up so that the overall state is has the right symmetry properties under particle exchange. And so that means if A and B are the only things describing the states of the particles, then the wave functions are pretty simple. They're just going to be the inner products between the locations of particle 1 and 2, and our state, say the bosonic one. And see, it works out now that when we do this, we dot product this with this state, what do we get? Well, this will be R1 dotted into A1. Remember how tensor products, inner products work? You do the inner products between the individual Hilbert spaces. You just multiply them together. So this whole thing will be 1 over square root of 2. What's the first term? It's going to be a wave function associated with state A, and it's going to be coordinate R1. This is just A1, or sorry, it's R1, A1. R1, A1. Then, of course, it's multiplied by phi B R2. That's this R2 B2 thing. Then there's a plus sign, and now we have, it's a little bit different. It's phi A, right, R2, and phi B R1. Because now particle 1 is in state B, and particle 2 is in state A. So you have to be, so the 1 and 2 labels which Hilbert space you're in. So this R1 you would have to dot with the B state, because that's the B1 here. So you can actually write these in the opposite order, I guess. It sort of depends on your convention. But for me, so the 1 and 2 labels the particles, and each one has its own Hilbert space, and you want to dot, you want to dot within that particle's Hilbert space. So this R1 would dot into this B1 over here, and this R1 would dot into this A1 over here, because that's the ones that correspond to particle 1. And then particle 2 is sort of the same thing. So this is what you would get. This would be this dotted into this. The particle 1 is in state A, so that's the wave function associated with state A for particle 1 coordinate. This is state B for particle 2 coordinate, and vice versa. Now particle 2 is in state A and particle 1 is in state B. And you see, it doesn't matter which ones you label 1 and 2. If you exchange the labels, you get back the same wave function. So that's the bosonic one, and the fermionic one, of course, it's the same thing, except with a minus sign. Get 1 over root 2, phi A R1, phi B R2, minus phi A R1, or R2 rather, phi B R1. So, so that's how you do it. So to construct the appropriate states for two identical particles or more, what you do is, you decide whether they're fermions or bosons. And of course, we have the spin statistics theorem to tell us that, particles with integer spin are bosons and half integer spins are fermions. And that's the proof of that would require, is typically done in field theory classes. It's more advanced, so I can't prove that to you, but you just take it for granted that that's the case. And after you've done that, if it's a boson, then what you would do is you imagine that the identical particles have distinct labels, like 1 and 2. And then when you construct your wave function, you would just add enough linear combination pieces to make sure it's completely symmetrized, that when you exchange the labels of any of the particles, that the wave function doesn't change. That's for bosons. For fermions, you would anti-symmetrize, and you just make sure that when you exchange the labels of any two particles, that the overall wave function picks up a minus sign. And those are the only rules. And everything else, you can just do regular quantum mechanics as if they were distinguishable particles. Just you're working in this, it's basically, you're working in that same tensor product space. It's just that you're specializing the states that are either symmetric or anti-symmetric under particle exchange. And that's it. Otherwise, it's just regular quantum mechanics. Yeah. So let's write down the kind of consequences here of these developments. First consequence is that even without interactions, so even if you just have two identical particles that don't even know about each other, just hanging out somewhere, so even without interactions, states of two identical particles are not product states. You see, because we have to symmetrize or anti-symmetrize, what you get is states that are entangled combinations of particle 1 and 2 being in different states, A and B versus B and A. So as soon as you have identical particles, even two identical particles that are not interacting, their state is going to be some entangled state because they're identical particles. It won't be a product state. And again, if this terminology is not familiar with you, look back at the notes from last semester when we covered entanglement and stuff. So the other consequence is that the Hilbert space for two identical particles is, of course, the tensor product space, but not the full set, but it's just a subset. So Hilbert space is a subset of the whole tensor product space. And the subset is one in which the states are either symmetric or anti-symmetric under particle exchange. So a Hilbert space is a subset of this tensor product space that is either symmetric or anti-symmetric under particle exchange. And if we denote that particle exchange as some operator, P12, the other important thing is that you can't convert between one and the other. They're separate subsets, and any kind of dynamics we have in our system, any kind of Hamiltonian we write down, won't be able to convert from one type of particle to another. So if you wish, a statement of that might be that, you know, the Hamiltonian commutes with particle exchange. So we cannot convert between fermions and bosons. And so once a fermion, always a fermion, once a boson, always a boson under any kind of Schrödinger evolution type thing. Any kind of quantum mechanics we do, you can't convert between one and the other. So once you decide you're in that subspace of states that's symmetric, then you evolve within that subspace, right? And then, you know, for anti-symmetric, same thing. So those are the major consequences, and we'll sort of explore more of this later, but that's sort of a good place to stop. You can, of course, add more particles if you wish, not just two. If you have three, again, it's always pairwise. You can always think about it as exchanging the labels of two of them. If you exchange two labels of two of them, then either you get a minus sign or you get a plus sign. That's the two different kinds of states. And it's not any different in terms of the tensor product. You just, you know, you tack on another Hilbert space for however many particles that you have there. And then you just you either symmetrize or anti-symmetrize, depending on which kind of particle you're looking at. But yeah, we'll talk about what happens when you combine now spatial and spin degrees of freedom. Then, of course, you have to symmetrize everything, both the spin and the spatial part. So we'll see what happens with that next time.